Hey guys, Mr. Hallman here, and we're going to be finishing up with our lessons on polynomial functions with this video. Today we're going to continue with what we talked about last week with rational roots, and we're going to add on complex roots. So if you recall last week, we talked about how with polynomial functions, we don't necessarily have a specific process that we follow to solve the equation. Rather, what we do is we try and generate possible solutions, and then we check them by plugging them in and using synthetic division. And we talked about the fundamental theorem of algebra, which told us how many solutions we should have is always equal to the degree of the polynomial. And we talked about how it is that we generate those rational roots, and we'll come up with that list and we'll see that checklist again here in a second. Today what we're going to do is we're going to add on, and we have this thing that's called the complex conjugate theorem. So basically what this says is that if we have a complex number a plus bi as a solution to a polynomial function or equation, we know that the conjugate a minus bi is also going to be a solution. So what that means is last week when we talked about our real and rational solutions, those are complex numbers, but the imaginary part is 0. Here we're going to see that there will be times when we get an imaginary solution. If I end up with, say, I as a solution to a polynomial, this theorem tells me I would also get negative I as a solution. So we're going to look at two examples of how this works. It's really going to carry over the same way that we did the rational roots last week. So before we jump into our examples, let's remind ourselves of how do we generate those rational roots. Alright, so before we jump into our examples, again, these are the steps that we had last week for finding rational roots. Remember that basically we're going to create a set of values that we consider P over Q. And the P values are the ones that make the factors of the constant term of the polynomial. So we're going to look at the number that's at the end of the function. We're going to take all those factors. Those would be the possible P values. The Q values are going to be the factors of the leading coefficient. So whatever the largest exponent is, let's say it's a cubic polynomial, then we're going to take whatever the coefficient is of the x cubed term, and the factors of that number will be our Q values. And then we take the fraction P over Q. So we take all those numbers and we set up the ratios to determine what the possible rational roots are. We're going to test them by using synthetic division, as we talked about last week. And then once we find a rational root, normally we'll be able to get to a point where we can factor. And what we're going to see today is with complex roots, we sometimes end up with expressions where we might not be able to factor. So the question then becomes, well, how do I figure out what the solution is to that expression? And that's going to once again be something that we talked about before that we're going to have to dust off and apply in this situation. So we have two examples to go through. Let's jump into the first one. Alright, so here's our first example. We're going to find all of the complex roots of the function p of x equals x to the fourth minus x cubed minus x squared minus x minus 2. As far as finding complex roots, we start off the same way that we did last week with rational roots. I need to generate my list of p values and my list of q values. So the first thing we're going to do is look at p, which are going to be the factors of the constant term, which in this case is the negative 2. So that means my p values are plus or minus 1 and plus or minus 2. My q values in this case are going to be the coefficients of my the factors of my leading coefficient. Well, the leading term is x to the fourth, and in this case the coefficient is 1. So that would mean my q values are plus or minus 1. Therefore, if I put them together, p over q, it's basically going to be the same as my list of p values, plus or minus 1 and plus or minus 2. So now what we're going to do is we're going to test these roots using synthetic division. So remember, we set up our new synthetic division house, so that way if the first root doesn't work, I jump to another one. I'm going to put my coefficients in, which should be 1, negative 1, negative 1, negative 1, negative 2. And I'm just going to start by testing the first root of 1. So we go through the process. Bring down the first coefficient. So now 1 times 1 is 1, plus negative 1 is 0. 1 times 0 is 0, plus negative 1 is negative 1. 1 times negative 1 is negative 1, plus another negative 1 is negative 2. 1 times negative 2 is negative 2, plus another negative 2 is negative 4. Well, 1 didn't work, so I cross that one off the list. So now we're going to try another root. Let's try negative 1. So again, first coefficient comes down. Negative 1 times 1 is negative 1, plus negative 1 is negative 2. Then we'll do negative 1 times negative 2, which is 2, plus negative 1 is 1. Negative 1 times 1 is negative 1, plus negative 1 is negative 2. And now negative 1 times negative 2 is 2, but plus negative 2 is 0. So in this case, hey, that one works. So that means I'm going to factor out of my function x plus 1. Remember the opposite sign of what I see for my root here. And then the leftover expression in this case would have coefficients of 1x cubed minus 2x squared plus 1x minus 2. And now what I'm going to look at is either doing synthetic division again, or I might see if possibly I can factor by grouping. So I'm actually going to put parentheses around the first two terms and the last two. So let's see. Now I would still have the x plus 1 out in front. And change this to brackets, because out of my first set of parentheses here, I can factor out a GCF of x squared, and the leftover would be x minus 2. And then out of the 1 minus 2, I can only factor out a positive 1, and that will leave me x minus 2. So now when I check here, the leftover expressions are both x minus 2, so that's a good thing. So what we have is x plus 1, and then the GCFs would be x squared plus 1, and then the x minus 2. And here's where the complex root comes in, because I'm going to set each of these equal to 0. X plus 1 equals 0, or x squared plus 1 equals 0, or x minus 2 equals 0. Oops. Not 20. X minus 2 equals 0. So the first one, x plus 1 equals 0, that means x equals negative 1. That's straightforward. The last term, x minus 2, that means x equals 2. The problem is here in the middle. X squared plus 1 equals 0. If I were to try and solve that, it doesn't factor because it's a sum of squares. And there's no x term, so I'm really not going to use the quadratic formula. Instead, what I would try is the square root property. So I would subtract the 1 over, and then I end up with x squared equals negative 1. Well, if I take the square root of that, that's going to leave me with x. Remember, anytime we take a square root, we get the positive or negative, and I get plus or minus the square root of negative 1. But if you recall, remember the square root of negative 1 is I. So really, this means x equals plus or minus I. And that's where we have the complex conjugate theorem coming into play. Because not only do I get I as a solution, or 0 plus I also get negative I, or 0 minus I. So those complex conjugates there. And that means my total number of solutions in this case is 4. I get the negative 1, I get 2, and I get plus or minus I. So 1, 2, 3, 4 roots, which the fundamental theorem of algebra tells me, because my largest exponent here was 4, that tells me I should have 4 roots, which is what we ended up with. So this would be an example of how complex roots work. We end up having to take the square root of a negative number, we get the imaginary, and we make sure that we have both the imaginary number or the complex number and its conjugate. Let's take a look at one more example. Alright, so here's our final example. we want to find all the complex roots of x to the fourth minus 4x cubed plus 7x squared equals 6x plus 18. Now, if you look at this, you might notice that there's something that's wrong with this setup. And the fact is that we don't have everything on the same side. So the first step is going to be to subtract over the 6x and the 18 so that we get all of our terms on the same side. All right, so now what that leaves us is x to the fourth minus 4x cubed plus 7x squared minus 6x minus 18 equals 0. And now we're going to go through, we're going to find our p over q values, and we're going to test them, and we're going to try and get down to our final answer. So if you want to pause it and you want to try that on your own, go ahead. Otherwise, I'm going to keep going. So if we look here, before I even list my p values, when I see that my leading coefficient in this case happens to be 1x to the fourth, that tells me that my p over q values are really just going to be whatever the p values happen to be. So in this case, I can just go directly to p over q. And the p over q are going to be my factors of negative 18. So I'm going to have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. And I'm going to start by testing them to see if any of them work. So I'm going to set up my synthetic division. And let's say we put across the top, we have 1, negative 4, we would have 7, negative 6, negative 18. All right, so let's start by testing 1. I'm going to try 1, bring down the 1. 1 times 1 is 1, plus negative 4 is negative 3. 1 times negative 3 is negative 3, plus 7 is 4. 1 times 4 is 4, plus negative 6 is negative 2. 1 times negative 2 is negative 2, plus negative 18, that gives me negative 20. Didn't work. All right, so 1's no good. Let's try negative 1. So we bring down the 1. So we'd have negative 1 plus negative 4 is negative 5. We would have negative 1 times negative 5 is 5, plus 7 is 12. Negative 1 times 12 is negative 12, plus negative 6 is negative 18. Negative 1 times negative 18 is 18, plus negative 18 is 0. All right, so there's one that works. So I'm going to split this up. This now becomes x plus 1 times, my leftover would be x cubed minus 5x squared plus 12x minus 18. And unfortunately, doesn't look like that's going to factor by grouping. So I'm going to have to go to synthetic division again. So I'm going to set this up, and now I need my new coefficients, which would be 1, negative 5, 12, and negative 18. And I already know from the first go around that 1 did not work, but negative 1 did work. So what I'm going to do is right away, to check and see if there's a multiplicity, I'm going to try negative 1 again. So let's go through. Bring down the 1. Negative 1 times 1 is negative 1, plus negative 5 is negative 6. Negative 1 times negative 6 is 6, plus 12 is 18. Negative 1 times 18 is negative 18, plus negative 18. Thought it was going to work, but it didn't. All right. So we're going to have to try some other values. So let's say let's try negative 2. All right, so we're going to bring down the 1. Negative 2 times 1 is negative 2, plus negative 5 would be negative 7. Negative 2 times negative 7 is 14, plus 12 is going to be 26. Nope, this one's not going to work. So I'm going to stop there. All right, let's try positive 2. Bring down the 1. 2 times 1 is 2, plus negative 5 is negative 3. 2 times negative 3 is negative 6, plus 12 is going to be 6. And then 2 times 6 is 12, plus negative 18 is going to be negative 6. Nope, that one didn't work either. All right, so let's keep going here. Let's try maybe 3. Let's try 3 in this case. Bring down the 1. 3 times 1 is 3, plus -5 is -2. 3 times -2 is -6, plus 12 is 6. And then 3 times 6 is 18, plus -18 is 0. Hey, we found one that works finally. All right, so now 3 is also a solution. So now I have x plus 1, and I would have x minus 3. And then my leftover would be x squared minus 2x plus 6. And that's equal to 0. And at this point, now we've broken it down into 2 binomials, the 2 linear binomials here, and we have this quadratic trinomial. Now you might remember from our earlier video, I said anytime we get down to a quadratic trinomial, we're probably going to be able to factor and reverse FOIL. Problem here, x squared minus 2x plus 6. Think about your factors of 6. Are there any factors of 6 that would add up to -2? Because since it's positive, I'm going to have the same sign. My factors of 6 are 1 and 6. They add up to 7. Or 2 and 3. They add up to 5. So guess what? This does not factor. So if we can't factor, that's a problem. That means we have to rely on the quadratic formula. So -b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to have to substitute in here. So we're going to substitute in our a, b, and c values. In this case, the a value would be 1, b value is -2, c value is 6. So we would have the opposite of -2 plus or minus the square root of -2 squared minus 4 times 1 times 6 all over 2 times 1. So that would give us 2 plus or minus, doing some work in here, we would have 4 minus 24 all over 2. So this would become 2 plus or minus the square root of -20 all over 2. And if I simplify this now, we're going to have 2 plus or minus 2 square roots of 5i all divided by 2, which we can reduce each of these by a factor of 2. So really, this becomes 1 plus or minus the square root of 5i. And that's actually 2 roots because it's plus or minus. So 1 plus the square root of 5i, 1 minus the square root of 5i. So x could equal those. Or going back to here, x plus 1 equals 0. That means x equals -1. And here, x minus 3 equals 0. That means x equals 3. That gives me my 4 solutions again. Leading coefficient, or excuse me, the leading term is x to the 4th, so there's going to be 4 roots. We end up with -1, 3, and then our 2 complex roots in this case, 1 plus or minus square root of 5i. Those are our 4 answers. So even though it didn't work out to factor, we used the quadratic formula to help us. That gives us our last 2 roots. This week, you're just going to be practicing solving for these complex roots. If you have questions, please let me know. Send me a message on Schoology, send me an email. We'll have our weekly Zoom meeting on Wednesday at 1 o'clock. And otherwise, I hope you guys are doing well. I hope to see you soon, and take care.